Hi, John Chamberlain here for Fundamentals of Light and Lasers, Course 1. Today we're going to do Laboratory 1-3B, Laser Eye Protection Equipment. Alright, for this lab, you're primarily going to be using the formula to calculate the minimum optical density required for eye protection while you're working with lasers in your lab. Now, your instructor will give you the specifications for the laser that he would like you to use. We're going to choose, for our example, a 5-watt helium neon laser. So, we'll look up in our table a helium neon laser, which has a wavelength of 633 nanometers. And we'll say that we have a 5-watt laser. That's a pretty big laser, but if we can protect ourselves from a 5-watt laser, we'll be doing pretty good against probably anything that we can encounter in our lab. So, what will be the incident irradiance for a 5-watt laser? That will be, the power would be 5 watts, and for the area, we're going to use the area of a 7mm pupil. Okay, so what would be the area of a 7mm pupil? It would be pi divided by 4 times 7 millimeters squared, or 0.7 centimeters squared. That turns out to be 0.38 centimeters squared is the area calculation. And if you calculate that out, that'll come out to 13.16 watts per centimeter squared for E0. All right. And if you look up in table 3 of your book for the MPEs for the helium neon laser for 1/4 of a second, you'll see that the MPE would be 2.5 times 10 to the minus 3 watts per centimeter squared. All right, so we're going to put that now into our formula for the optical density. Log base 10 of that ratio of 13.16 watts per centimeter squared divided by 2.5 times 10 to the minus 3 watts per centimeter squared. And we'll see that the watts per centimeter squared cancels out. So we can put the ratio of 13.16 and 2.5 times 10 to the minus 3. Take the log base 10, and that calculates out to 3.7. So an optical density filters of 3.7 would be sufficient to protect our eyes for the blink reflex of 1/4 of a second of the helium neon laser. Okay, so we've done the optical density calculation for a blink of an eye. What would happen if we had a little longer? Looking back at table 3.3, if we looked at the maximum permissible exposure for 600 seconds, which would be 10 minutes, then we'll see that we can have as much power as 293 times 10 to the minus 6 watts per square centimeter. So we would change that value in our formula. 296 to 93 times 10 to the minus 6 watts per square centimeter. And I've done that calculation, and that would come down to an OD calculation of 4.6. So we would need a little bit more optical density eye protection if we were going to work with a longer exposure to lasers. How about that last column in the table? That would be 17.6 times 10 to the minus 6. And that corresponds to what? That corresponds to 3 times 10 to the 4th seconds. Does anybody know what that would be? 3 times 10 to the 4th seconds is about 8 hours, a little bit more than 8 hours. And that would require an optical density of almost 6 in order to give you sufficient eye protection. It turns out the goggles that we have here are labeled OD6 at 632 nanometers. Sure enough, these goggles are designed to protect our eyes for about 8 hours using a 5-watt laser, helium neon laser. So we could wear these. Derek and I could wear these and we'll be good to go for all day long using a helium neon laser. So that concludes Lab 1-3B, and I hope that you keep yourself safe around all the lasers that you work with in your lab.